Good afternoon or good morning, everybody, depending on where you are. Tim Lankish here from CAE Services. We'll get started in a couple of minutes as we wait for people to filter in here. So stand by, and we'll be getting started soon. Okay, so I have a couple people trickling in here, but we'll go ahead and get started. Again, my name's Tim Lankish. I'm the Director of Engineering here at CAE Services, and welcome everybody to our Ask the Moldflow Experts webinar series. The topic for today is Moldflow, back to basics. And today we're gonna focus on flow or filling analysis. This is me, my background. Some of you have probably seen this slide before. My background's in physics and math. Actually, I just turned over 29 years. I need to update that number there. I've been around the block, doing Moldflow for a long time, training people in Moldflow to be expert certified engineers. I've contributed to trade magazines and presented several times at the Moldflow Summit. There's my email address if you have any questions after today's webinar that you'd like to ask me. CAE Services also has been around quite a while. We were established in 1988. We have the most expert certified Moldflow engineers in the world. We are an Autodesk partner, and we've completed upwards of 30,000 plus projects now in our consulting business. Here's our website if you want to learn more about our company, caeservices.com. And this is our technology center out in the suburbs of Chicago. So just a quick recap of our last webinar. We're doing this Back to Basics series. A lot of the webinars that I've done in the past have focused on very specific topics, warpage, part to print, appearance issues, any number of things related to Moldflow. And I thought it'd be a good idea to take a step back and for those people who maybe haven't seen Moldflow or wondering what it's all about, take it piece by piece and get back to some basics and explain each of the different types of analyses that we do and what is involved in doing that type of analysis, what types of problems can be solved, and how we can solve them. So in our last webinar, we did just a quick overview of that and went through a little bit of the Moldflow history. You see the different logos over the years there. We talked a little bit about what Moldflow can and can't do, filling, packing, cooling, and warpage analysis, and helping us determine or predict part quality to some degree. We talked about how the technology has evolved through mesher technology, solver technology, how people have used it strategy-wise when they've used it as either a band-aid approach after a mold has been built and parts are being made, or the best time to use it, which is way ahead of cutting steel on a mold. So, and I would argue that it's probably been one of the technologies that has had the most influence on the industry and on the plastics industry over the last 40 years or so when it was founded. So it's an important technology, but it's a technology that a lot of people maybe have seen but don't quite understand how it's done and what are its uses and limitations and so forth. So that's what this series is all about. And the idea is to enable engineers to predict, identify, and solve problems, molding problems, and I would argue avoid them altogether if we can. The benefits have been well documented, on the filling side, improving gate and filling patterns, balancing pressures, improving packing, establishing cooling uniformity and making our cooling designs more efficient, and then identifying and solving warpage problems. Those are the basic ideas or basic areas where Moldflow has really shined and it's been well documented. And again, it allows engineers to solve problems. If it's an existing tool, identify the source of the problem, and if it's on new tools, then we can play what if. Maybe we can push the envelope a little bit on part design or what have you. So that's the idea behind using the technology, is to predict, identify, and solve problems. So today's focus again is on the filling stage, and we're going to focus on the filling stage. It'd probably be a good idea to define it. So here's just a quick flow chart that describes step by step what happens during the filling stage, right? So we have the injection mold hung in a molding machine. You see the screw and barrel system with the hopper feeding raw material into the screw and barrel system. The mold closes, the screw moves forward. As that screw starts to move forward, the check valve closes and it keeps material from moving back into the screw and barrel system where material is being heated up, and both by friction and by heater bands. And then that material is forced into the mold as the screw moves forward at some prescribed speed. We keep filling until the mold's filled about 95 to 98%. And then we stop at that point and we switch over to packing control. So we start with velocity control and then we switch over to packing. And we won't discuss packing today. It's going to be strictly limited to the first stage of filling. We'll talk about packing in our next webinar. So our primary goals, the big picture here is several things. Obviously the big goal here is we got to be able to fill the part. If we can't fill the part, then we don't have a part, so to speak, right? So that's our primary goal. Other goals, we want to avoid aesthetic problems in many situations. Not all situations require this, but many cases that is true. We want to avoid knit lines or flow lines. We want to avoid air traps, which can cause shorts, voids, or burns. And we want to avoid gate blush. Those are three of the most common aesthetic problems that we encounter in the injection molding process. We also want to set up conditions so that when we move on to the pack and warp stages, or pack and cool stages rather, we want to set up conditions where we can avoid shrinkage problems and warpage problems. So that's one of the things that we have to develop while we're in the filling stage even. And then ultimately, we want to develop a large processing window. You see that on the right. So there's three main variables that control that process window: melt temperature, mold temperature, and injection speed. So because there are so many variables involved, and each of those variables in the injection molding process involve some level of uncertainty, whether it's lot to lot variation for your material, or a leaky check valve on your injection molding machine, or any, you name it. There's probably 100 different variables you could name that are involved in the injection molding process, and not all of those can be necessarily directly accounted for in the mold flow process. So what we want to do as analysts is provide the largest possible injection molding window, processing window that we possibly can, because we know there are going to be things that we can't directly account for. And so we don't want to have to hit a target so small that if any of those things comes up and puts us out of that small window, we can't mold apart the way we want to. So it's our job to develop gating, to develop processing, and so forth, to get the largest processing window we possibly can. So in order to do all this, we have to be able to get good answers out of mold flow, right? Mold flow, in some cases, gets a bad reputation because results don't match what they're seeing at the press, and oftentimes there's very good reason for that. It is a simulation technology, and there are 4 different main items that are input into our simulation models, and if it's not done properly, then you're likely to get poor results. The first step is we have to mesh the part, and that's going to come in one of 3 forms, and we'll talk about that in a minute, but midplane, dual domain, and 3D tetrahedral. We have to define a melt delivery system. We have to give gate locations. We have to define the upstream geometry. We have to decide hot versus cold runners. We have to have material properties that are input into the simulation model. And this is probably one of those areas where garbage in, garbage out rears its ugly head, because there are many materials in the mold flow database that aren't necessarily fully characterized. So we'll talk a little bit about material properties as they relate to filling analysis. And then lastly, the process settings. We have to get a handle on temperature, how we're going to control temperatures, how we're going to control fill speeds, and how we're going to, if we have a valve gated system, how we're going to control valve gates. So all of these things have to be well defined in order to properly simulate the process. And if we properly simulate the process, we can trust the results, and by trusting the results, we can solve or avoid problems. So talked about meshing the part. Here you see the part on the left modeled up in CAD, and there's different ways to represent that. We have midplane mesh, which is how mold flow started as midplane meshing, where we take the outer and inner surfaces, model a third surface halfway between those, and assign wall thicknesses according to whatever the local wall thickness is of each of those areas. This is the fastest, most efficient way to do things in mold flow, and allows us to do a lot of simulation in a very short period of time. It is our go-to mesh here at CAE Services, but there is some uptime modeling work that needs to be done, or upfront modeling work that needs to be done, and it takes some time and effort to do that. Recognizing that, mold flow at some point decided they want a more convenient mesh because engineers were getting, I guess the best word is frustrated, trying to create midplane meshes all the time, and taking a substantial amount of time. So they came up with dual domain mesh, and this is a process where we're actually meshing outer and inner surfaces directly, and then in the background, it uses what I call the buddy system, where it matches mesh from one side of the a given wall to the other, kind of figures out the midplane from there, figures out what the wall thickness is, and then essentially runs midplane analysis in disguise, so to speak. But you can see there that in many cases, you don't have as good a control over how that matching process works. And if you don't, then maybe you need to recondition your part to allow the matching process to work out a little bit better. Those areas in blue are well matched. The areas in red are not well matched. So it doesn't, it's not calculating the wall thickness well in those red areas. So in some cases, mid-plane's better because you have a little more control. In other cases, you know, maybe dual domain mesh will work for you if the part geometry is a little more simple. And then we get into cases where we have thicker, chunkier geometry. This isn't necessarily one of those cases, but the geometry in that reflector area is relatively complex. So getting a better handle on complex filling patterns through complex geometry like that is one area where 3D tetrahedral meshes really shine. But there are some drawbacks to that too, you know, and warpage on the warpage side and so forth. And it also costs you quite a bit of time on the solving side too. So advantages and disadvantages to each one of these. I'm not going to go into great detail on that here, but just know that you know, when we build our simulation models, we have to pay a lot of attention to the mesh, how we mesh it, mesh densities and so forth, which type of mesh we pick to get the answers that we're looking for. And here's one of the consequences of using a poor mesh. You know, if we don't mesh it densely enough, you might miss a knit line like we're seeing here, right? 1 million elements, which sounds like a lot, didn't catch that knit line in the corner there. 3.3 million elements did. So knowing what type of mesh density are required to get the answers you want so that you don't get false positives is a necessary component of building our simulation model. Talked about material properties. For the filling process, there are really three main components to this. And you know, if you wanted to assign some weighting to this, I'd say 95% of it is the rheology curves that you see on the left. So it's describing the material's viscosity, which you see on the y-axis there on a log-log scale, versus shear rate. So how the material is shearing, which is related to the fill speed, of course, and to the wall thickness, how the viscosity changes as a function of shear rate, and also how it changes as a function of temperature. And you see the different temperature curves there. So viscosity is a product of shear rate and temperature at its basic level, and that these are the curves that govern the flow behavior of the material as it passes through the runner system, the gate, and the part. The second picture you see there is called juncture loss. This accounts for pressure losses as we have changes to diameter through the runner system. I won't go into great detail there, but this can matter to your pressure predictions. And if we're going to determine whether or not we're able to fill your mold, then we have to know how much pressure it's going to require and compare that to the limits you have on your injection molding machine. And then lastly, this is not something that many materials in the Moldflow database actually are characterized for, but it's called pressure dependent viscosity. This gets into areas where we have very high pressure molding, tends to exhibit this type of behavior on like polycarbonates, PCABSs, very thin wall geometry, long flow lengths, high pressures, et cetera. So this can add to the pressure requirement as we get up into those higher pressure situations. And here's some of the consequences of having poor material data. For example, this one, you're comparing what happens if you have juncture loss data versus not having juncture loss data. You see the difference in the pressure prediction there. Same filling pattern, same everything, same process settings, same runner system geometry, but the juncture loss data was missing. And you can get yourself into situations where, again, you get a false positive. You think you're going to be able to fill this mold, but in reality, you know, with all this additional pressure loss through the runner system that you didn't account for, it may end up biting you when you go to a mold tryout. So again, important to have good material data. And be very careful if the material you're molding isn't in the material database. You got to be careful how you're substituting if that's the route you decide to take to account for that lack of material data. So that's the predict end. We gotta make sure we have good information going into our simulation model, and so that when we start simulating things, we can trust results and then use that information to help identify potential filling problems. Okay, so that's the next stage. So you see some of the problems that we could potentially have over there on the right. So like a backfill situation in that upper left corner there, because that little membrane is very thin compared to the rest of the part. Knit lines or flow lines. You know, I talked about pushing the envelope a little bit earlier there. This graph on the bottom shows the relationship between reducing wall thickness and the pressure. As you see, we go farther and farther to the left on the curve, the pressure goes up as the thickness of the part decreases. So, you know, in some cases that may cause a non-fill. You know, the part's too thin, or maybe we don't have enough gates. Maybe we have a very stiff flowing material. Maybe our runners are too small, or maybe the runners are too long. Maybe the injection molding machine has too low of a pressure available. So all of those things, we can use Moldflow to identify what's causing a particular problem, in this case non-fill, and then go about figuring out what it's going to take to fill the part. So that's one issue. Non-fill flash can occur even during filling, in cases maybe where you have clamp force exceeding the value of the injection molding machine, the limit of the injection molding machine. That can happen during filling if you're using too few gates, or again, if you're pushing the limit on part thickness, going too thin, any number of things. If you don't have balanced fill, you know, flash can occur. So sometimes it's a tooling issue, but in many cases, it's related to pressure, and that pressure can relate to any of those things that we talked about earlier. And then we have appearance issues, of course. Gate blush, you know, that can be caused by gates being too small, or filling too fast, or not having enough gates, not sharing the flow among gates. Flow lines, that can be caused by melt hesitation and acceleration when you're using a valve gate sequence. We could have knit lines, you know, flow around holes in geometry. So, you know, maybe we need to redesign where those holes are. Maybe we need to try to locate our gates and use valve gate sequencing to put knit lines in less conspicuous areas. And then we have air traps. You know, that's typically a part design issue, thick versus thin, melt behavior, flow behavior through those areas adjacent to one another playing out. Or maybe we have an air trap at a parting line and it's not being vented well, so we need to put venting where that air is trying to get out. Here's just some examples. You may have seen this before, but you know, there's a knit line that was forming. It's pretty obvious why it was forming, is because they didn't really do much to move gates around or fashion the part geometry to move the knit line. They were probably just hoping for the best and hoping that knit line wouldn't be too visible, but of course it is. Moldflow confirms that. And here's the nominal wall thickness that the part was designed to. So to fix that, to move it, you know, a better solution probably would have been gating in a different area, but the mold was already built. We confirmed, you know, that the knit line could move if we changed wall stock. So we had to build some flow leaders into those orange areas there, make them thicker, and then we thinned it out in that green area there to help guide the flow and put the knit line in a less conspicuous area. So again, so we start off with getting the results right, making sure we have a good simulation model, which helps us to identify any number of problems that we see in filling, and we listed out several of them. And now we got to develop a strategy to solve the problem, or in the case of a mold that's not built yet, to avoid the problem. So we start off with gate locations and determining not only where they are, but how many do we need. And we're usually going to do that in a brand new mold without even building a runner system. We're just going to put some points on the part, as you can see on the right, and play around with different locations until we see good balance. As is the case with everything in injection molding, there are trade-offs, and you can see one of them there pretty clearly on the right. Balanced gate locations with 3 gates there is going to produce an air trap in the center of the tool. So what might be good for pressure and clamp force may not necessarily be good for other things like air traps and so forth. So it's always this constant balancing act, playing around with things until we get the best of all worlds. And in many cases, we're not going to get there in terms of being able to achieve all of the objectives you set out to achieve. Sometimes you have to prioritize them and maybe put something else a little bit lower on the list. In this case, maybe we do need to go to more gates, or maybe we need to go to a valve gate sequencing strategy, something like that. But in any case, one of our goals is to try to balance the flow as much as we can, because it helps us to keep pressure at a minimum. And like I said, we're going to use valve gate sequencing if necessary, or if it's in the budget for the tooling budget. We're going to move gates around until we get the knit lines where we want them, and we're going to try to eliminate air traps as much as we possibly can. So that's what's involved in locating our gates. Get the right number, get the right location, so we get the right filling pattern at the minimum pressure and clamp force that we possibly can. Once we've got our gates in line, now we got to focus a little bit on the process, and we're going to start just by looking at the process in the part cavity itself. So we want to determine the best mold and melt temperatures and the best fill speed to achieve that. And one of the goals there is to maintain a uniform flow front temperature, so that we can set ourselves up for a situation where we're packing the part more uniformly. And then once we've got process conditions laid out, then we're going to design a melt delivery system so that we size gates and we size runners properly to get the conditions in the part cavity that we were looking at, when we were laying out our process. So, for example, over here, one of the process things that we do is we do a fill time scan and see what the relationship is between injection pressure and injection time, and we can get a feel for where we need to be with our fill speed. So just to look at some different ideas here. So, we talked about flow balance, right? This is one of those trade-off situations. Balanced flow with all these drop locations that we did early on, but it puts a giant knit line right in a visible area like this knot pocket. So we had to change course and go with a valve gate, sequenced valve gate solution. Start by firing this gate at the bottom of the part, let the flow pass through that area, and then fire the rest of the gates in the non-show areas. So again, it's that trade-off between objectives. I'd love to have balance and reduce the pressure, but can't do it at the expense of having a giant knit line in a visible area. Here's another knit line placement situation. Symmetric part, we want to be able to fill center out, but we've got all kinds of appearance surfaces that we have to deal with. And so we were able to not only get a valve gate sequence that we want to keep knit lines off of the appearance surface, and you can see where all the knit lines occur here, but we had to be a little creative with how we changed our part design on this too. We had to institute a flow leader and flow restrictor side by side to guide the flow left to right as it was kind of passing through into the appearance surface area. So I talk about this all the time, but I like to try to hardwire solutions into a part design where I can. I don't want to have to rely on process to try to fix a problem at the press. I'd rather just hardwire it in there, and this is one of those ways to do it. Building flow leaders, flow deflectors into your part geometry. This passes on to the other types of analysis too, pack, cool, and warp, and we'll talk about some of those things when we have the other webinars. But trying to get as much hardwired into the part and mold design as we can is a good thing. It opens our molding window. So another type of knit line, if you want to call it that, and it's not really a knit line, it's called a flow line, but it looks an awful lot like a knit line. This is a blemish that occurs because of acceleration of the melt front when you're using valve gate sequencing, for example. So in standard valve pins, you know, those nozzles are pressurized, and the valve pins retract very quickly and allow a rush of flow through those nozzles, and so it accelerates the flow front in those areas and causes this flow line. So the material starts to bunch up there, and then all of a sudden it takes off from that point forward, and you see a little bit of a flow line at the surface. So the solution to that is to use velocity controlled valve pins, and that's one of the controls that we have available to us in Moldflow. Pretty much all the big hot runner suppliers these days have some version of this velocity control, so not hard to find out there in the industry. But here's what it looks like in Moldflow. For standard valve pin retraction, you see these flow contours developing as the material flows across the part. So it starts to hesitate, and then it accelerates as the next set of valve gates opens as we move across the part. So we're using valve gates, which is a good thing to avoid knit lines, but if we set it up like this without any valve pin control, then we can expect some flow lines. So when we went to velocity controlled valve pin retraction, you see these flow contours are much nicer in terms of how they're spaced apart from one another. In some cases, we don't have part design changes available to us. This is a medical application here, and there was no option to change wall stock on that center area there. So we had to use processing in this case. And again, I don't like to have to do that, but in many cases we do have to do that. So, you know, even at a relatively fast fill speed of 1.1 seconds here, it's developing this backfilling condition in this inner geometry feature here. By filling it twice as fast, essentially, almost 3 times as fast, you can see we're able to change that air trap into more of a knit line. You still see some major hesitation there, and this thing is really just screaming for a wall thickness increase. But short of being able to do that, we can mitigate that with a little bit faster fill speed. Another way to take care of air traps is to change the part geometry. In this case, we actually move these wells closer to this gate on the left. And by doing so, we were able to get the flow front to move more uniformly across those and eliminate the air trap. They were more concerned about the air traps in these giant wells than they were in the smaller ones. They were still going to get air traps in these. And when you have a tall, narrow core like you see in these areas here, you're likely to get an air trap no matter what. But in this case, we were able to just move, at least for the large wells, move those over to a different position. That was okay with them to try to help fix that particular air trap. Another thing we do with gate location is affect the fiber orientation. And this is not a webinar about warpage, but you know, we talk about trade-offs. as we move gates into different positions to affect the fiber orientation and improve the warpage, we have to be looking at things like pressures and so forth, because oftentimes what's good for warpage is going to put you in a position where it increases the pressure and the clamp tonnage that's required to fill from a different gate location. So we have to be monitoring that during the filling stage as well. This is also an issue with two shots, right? Two shots. You see the first shot on the left. If we wanted to balance the flow on this, we'd put a gate right in the center of the part, but we can't gate in an appearance area, so we have to move that gate off to the side. And in this case, we're able to put it in a position where it's going to be overmolded by the second shot, so it hides that gate vestige, which is a very good thing. And we're able to, get a reasonably good filling pattern without any kind of air trapping. We have to monitor the pressures and so forth to make sure that, this longer flow length isn't causing pressure and or clamp tonnage issues. And then with the second shot, notice what's happening here. We've got a knit line forming, and then it's pushing air back towards that first shot. We don't want that. That air cannot be vented there. Here's showing this little V-shape air trap here. So we actually ran this both in midplane and 3D, initially in 3D, but then built a midplane model so we could start playing around with different flow leaders to try to get rid of that air trap pattern. And you can see what we did here. We just played around with the mesh, changed some thickness values in our midplane model, and we're able to get a filling pattern that we then confirm back in 3D to get that knit line and air trap back out to the parting line where it could be vented. And when they molded these parts, you can see that they were able to get that, confirm essentially what Moldflow was telling them there. Part of the filling analysis process is selecting a gate style, and you see a myriad of different gate styles there: edge gates, sprue gates, fan gates, flash gates, sub gates, cashew gates, pin gates, and hot drops. And the three main factors that go into deciding what type of gate to use are, how the mold's being constructed, of course. Cost is an issue. Do you want to go through the expense of building a hot manifold, using a hot manifold? There's upfront costs there, but there's benefit down the line and less material costs and so forth. So, there's cost-benefit analysis there. Appearance issues: can we have a visible gate vestige? And maybe in some areas yes, maybe in some areas no. So that plays into it, where we can and can't gate. And then degating is a big thing, of course, whether or not you want the expense of manually trimming the gate, or if you need automatic degating. So all of those factors go into determining whether or not, or what type of gate you're going to use on your particular mold. But no matter what is chosen, we have to size the gates properly, and how we size them is going to depend heavily on that type of gate. Sub gates and pin gates are some of the most difficult ones to size because they tend to be very small. But again, we have that trade-off, right? Big benefit in degating, but in order to automatically degate, they have to be relatively small. And when they're relatively small, you risk having too much shear through those gates, and consequently could end up with gate blush. So our goal in Moldflow is to try to minimize those shear rates in whatever way we can, whether it's through gate sizing, increasing the gate size, maybe it's decreasing the filling speed, but again, trade-off, right? If we decrease the filling speed, we might subject ourselves to the possibility of not filling the part. So we have to determine the number of gates that we might need to reduce that shear rate and shear flow among all the different gates. But now we're opening ourselves up to the possibility of knit line. So all of these things are interrelated, and we have to again, prioritize our objectives and see which ones we can, see how many of them we can satisfy simultaneously. But you see what's happening here in these two pictures up top. So with that small, tiny little cashew gate, we have 361,000 reciprocal seconds. That's well above the material limit of 100,000. And then when we switch to a rectangular cashew gate, that with a little bit more thickness and width, that allowed the shear rate to be reduced considerably and well below the material limit. And we do try to stay well below that material limit. These are relatively generic numbers that come out of Moldflow database. They're not specifically tested for, so we need to stay well away from that published material limit. And you can see we have the ability to track the shear rate throughout the cycle. And I put this one up here to kind of illustrate what happens in a valve gauge sequence situation. You know, the first gate to fire is the one that sees all the flow coming through one gate. So you see it's the one that shows them the most amount of shear. And then the ones, as they turn on in succession, start to share the flow, and all the shear rates tend to come down from there. Many cases, we're going to get into a situation where we need to balance the runner. Not a big advocate of putting very different sized parts in the same family mold, but it does happen. And in some cases, we have to balance not only the hot manifold, but also the cold runners to get the kind of flow pattern we need, where both cavities are filling simultaneously, so that we get relatively similar pressures in those cavities, so that they have a chance to pack out more uniformly between the two. In the case of multi-cavity molds, where we have all the same parts, but we don't have a balanced runner design, some artificial balancing of cold runners would be necessary as well. And we also have to develop a process, and one of the things that we do is run a fill time scan on just the part cavity to see how much you know, injection speed we want through the part cavity itself, and we can see the relationship between injection time and the pressure required to move that material through the cavity. So we run different injection times. We also do this once the runner and gate are on the geometry as well, just to make sure we're kind of in a sweet spot for keeping our pressures at a minimum. But along the way, we have to monitor flow front temperature simultaneously. We're looking for the material not to heat up too much, i.e. shear heating, and we're also trying to maintain a speed that won't allow the material to cool down too much either. If we cool down too much, then you might get a non-fill in some areas, but you also set yourself up for a situation where the part's not going to pack out uniformly. So those are the conditions we're trying to set up when we develop a process. We want to try to allow the material to pack out uniformly, but do it with minimal pressure. So we got to find, again, the right fill speed that's going to allow us to do that. And if we can't find it initially, that might be telling us we need more gates or something. It could be any number of things. Or maybe we've designed the part too thin, or whatever it may be. So that's kind of it in a nutshell. I talk about this at every webinar, but things we're doing at CAE, we've added feasibility to our services list. Feasibility studies can often help us identify part design problems before they stick out like a sore thumb in Moldflow. We'll just say it that way. We are Autodesk partners. We are resellers of the Moldflow software. We train people to be expert certified, and we mentor people along the way. We have both classroom and online training. We're doing these Ask the Moldflow experts on a monthly basis, these webinars. So keep looking for these. The next one we have is going to be dealing directly with packing analysis, and then we'll follow that up with cooling and warpage in the months ahead. Moldflow office hours are available anytime you guys want to spend time with me or one of our engineers to talk about whatever Moldflow topic you want. you know, sign up for a time to do that. We can spend some direct time with you on that. And then again, there's our website. So I'm going to open the forum here to direct questions, live questions. Been trying to keep these particular webinars a little bit shorter, but there was a lot to talk about for filling today, so I apologize for that, but I thought it was important to put all that in there. Does anybody have a question? And if you do, here's how you do it. Raise your hand and we will unmute your mic, and then you can ask the question live. Always takes people a little bit of time to get rid of the shyness. Faisal, let me unmute you here. You might have to unmute yourself there. If you can see this button on your control panel, click that so that it goes green.
Yeah, can you hear me?
I can hear you.
Yeah, thanks for a good presentation.
You're welcome.
Yeah, I have one question, like the gate locations and gate sequencing. Okay, my experience based on like a few large flow, mode flow exercises we have to working on some part design. So there's a lot of hit and trial method. Mode flow expert basically do this way, and they find out sometimes they were surprised. Okay, we have big pressure drop and tonnage drop. Just working when we start working, maybe 20 attempts, maybe close to, we have very good drop happen. I'm very surprised, same sequence, no, same gate locations, but different sequences. So is mode flow give us some optimum design also, like optimum sequence? Give you, okay, I go with this way, it's like reverse engineering, kind of things. So we can have because this is all based on experience, where you do multiple hit and trial method, then you find out, that it take long time, okay, do all this analysis, right? So this is a question coming up my mind, if it's possible to have this kind of reverse engineering, so you have to save the time, during mode flow analysis.
Yeah, I mean, when it comes to determining the optimum filling sequence, there is a trial and error method, and that's one of the reasons we opt here at CAE to use midplane models, because we can do a lot of simulation in a short period of time. If you're building full 3D models and you're using valve gate sequencing, and it takes a long time to run these models sometimes. So, so choice of simulation model type is important to be able to run a lot of simulation in a short period of time. But I mean, there's nothing in Moleflow that you can set up to say, can you automate this process to give me an optimum filling sequence? Because the optimum filling sequence is different for different people. I could put a large part in front of 10 people and have them all give me their opinion on where knit lines need to be and where the gates need to be, and I'm going to get 10 different answers. So that's why we simulate a lot of different things, because of this whole idea that there's a lot of trade-offs. If we have knit lines here, then it's going to drive pressure up, or if we need to move a knit line over there, it's going to change the filling pattern or the fiber orientation pattern, which is going to affect the warpage. So there's all these trade-offs, and I guess, I don't know if unfortunate is the right word, but it's unfortunate that sometimes you do have to run a lot of iterations. It's not uncommon. It's not uncommon for us to be running upwards of 50 iterations on a very difficult mold, large part with lots of knit line concerns, for example.
Yeah, so that's why maybe we can look for some artificial, intelligence involved here. Maybe, honestly, this is really a lot of time consuming. Sometimes we receive a report after 1 week, to have some decision. Okay, so really, sometimes you can't make a quick decision here. Huh? So
yeah,
this is one limitation here. Huh?
And I think the best way around that is, or for now anyway, is to use quicker models and to use people that are able to do this type of analysis work relatively quickly, right? So there is no artificial intelligence algorithm or whatever that's going to give us the best sequence at this point. But we've seen a lot of these molds, and we're able to as expert analysts ourselves, we're able to kind of jump to a better conclusion a lot quicker than maybe someone that's less experienced at mold flow might be able to. But thank you for the question. Good question. Anybody else out there have a question? Marco, go ahead and unmute your phone there.
Okay, can you hear me?
Yep, I can hear you.
Okay, perfect. First of all, thank you to the team for the explanation. I have one question that probably is not only oriented towards topics about feeling. It's more about prediction capacity of mold flow. And my question is basically if you have some kind of rule of thumb or something like that that we can follow to estimate how big is the variation expected of the prediction that mold flow is making. Let me give you an example. Let's say that we have predicted that we will have a needle line in certain position. And if you have, I don't know, a range in which this position can vary in the real model.
Well, a lot of it is how you're setting up your process relative to mold flow and the criteria you're using. Let me go back to this situation here. For example, yeah, this one right here. So when we set this up in mold flow, oftentimes we're going to use timers in mold flow to tell these nozzles when to fire, or we can use flow front position. We can say, okay, when the flow front of this filling pattern gets back to this certain nozzle, go ahead and fire that nozzle. So maybe we want to backfill the runners, or maybe we want to trigger it at some other location for some reason. So the mold flow output is going to tell you the time at which each one of those nozzles fires, even though our criteria was flow, allow it to flow back to the nozzle. So then we get to the mold tryout and we try to start setting this up, and someone looks at the times and tries to set the nozzles up so that they fire at specific times, and then the knit line's off, for example. So you have to, when you're at the press, you need to run a short shot sequence study to confirm the precise moment when the flow front gets back to the nozzle, for example. So make sure that you're doing those types of things at your mold tryouts so that you're getting visual confirmation of the filling pattern so that you fire these nozzles at the right time. Most people are going to fire based on position, the screw position. That's how they set it up at the press typically. It's a little more difficult to calculate that from the mold flow output unless you have the screw and barrel diameter. But even then, there's some compressibility things that there's some initial compression of the material that goes on in the screw and barrel that's not necessarily directly accounted for in mold flow. So use short shot progression studies at the press to make sure that that's how you're firing your nozzles. That's the best advice I can give you there. But in terms of giving a range, I don't know that there's ever been a real study like saying, okay, most of them are within a couple of millimeters or within a couple of inches of their initial location.
Okay. And for example, in terms of pressure, let's say, is it like a safety factor that we should apply to be within the safe range?
Yeah, so there's, I mentioned earlier, there's a lot of things that aren't necessarily directly accounted for in a mold flow model, right? Leaky check valves, I can't account for that. Oftentimes we have the injection nozzle itself on the machine that we don't know the geometry of. There's a pressure drop associated with that. you know, it's not unheard of to see upwards of 5,000 psi pressure drop through the injection molding machine nozzle. More typical numbers would be more in the 1,000 to 3,000 range. So you have to account for those things as well, and that's precisely why we don't want to run our pressures right up against those limits. We want to stay well below that because we know there are things that MoldFlow isn't able to directly account for. So to correlate well with MoldFlow, you'd have to have a very well instrumented mold with pressure sensors at the right locations to be able to directly compare to MoldFlow output. But my best advice on that is to stay away from the high temperatures or high pressures rather as best you can, and use MoldFlow to do it. You know, stay 5, 7, 8,000 psi below your machine's limit, and you should have enough to account for, you know, the other pressure drops that MoldFlow is not directly accounting for.
Mm-hmm. Okay. Yeah, I got it. I think that probably the best for us, it's going to be to try to take into account all those kind of variations and try to, let's say, I don't know, characterize our machines, because we run mostly of all of our tools in-house. So probably what we can do is to try to make this kind of correlation, but based on the actual equipment in which we run those tools. And probably in that way we could set up the limits specifically for our plant. But yeah,
right. Yep.
Thanks a lot for your answer.
Yeah, and again, as analysts, we're trying to create the largest possible injection molding window we can, processing window. And so many people try to push the envelope, you know, with part design too thin, too few gates, you know, don't want to spend the money on an extra hot drop, whatever it may be. All of these things contribute to making your molding window smaller and smaller. And I get it. It's a good thing to push the envelope, but don't be surprised when you push it a little too far, right? So use the technology to get you to a point where you've got a satisfactory molding window without pushing the envelope too much. Okay, anyone else have a question? Just have a couple of minutes left here. I did have a question that was submitted before the webinar, and somebody asked the question, can you simulate venting? And the short answer to that is yes, but we generally don't. One thing you should know about MoldFlow in its standard format is that air gets out wherever it needs to. So it will tell you where the air is getting out in the simulation, and the hope there is that it gets out at a parting line so you can vent it, or you know, worst case in an area maybe where you have an ejector pin that you can mill off and vent through an ejector pin or an insert or something. But in 3D technology, we can actually put vents in there and define the size of the vent and see how it affects the filling pattern. But haven't had real good success with correlating that when it sometimes can affect the filling pattern, but it can be simulated, but my opinion, it's a little iffy at this point. Got another question on the questions tab here. It says, is a 0.6 second injection time feasible for a 500 millimeter length flat part of 1.6 millimeter thickness when molding window is giving the same injection time range of 0.45 to 0.6 Vectra A130? Hard for me to answer that without actually looking at the results. Sounds very daunting. Obviously, you would definitely need very good venting on that tool because you're going to be pushing a lot of air out of there in a short period of time. So venting may come into play on that. But I would have to look at that a little bit more closely to give a better opinion. And again, very good reason to be using MoldFlow. Okay, any other questions? All right, well, thanks everybody for attending. Appreciate your time. I hope this was helpful. For those who have not seen these webinars before, hope you join us again. Next time we're going to be attacking packing analysis as we get back to basics. So, and then as I said before, we'll be moving on to cooling and warpage analysis in the months following. So again, appreciate your time. Thanks for attending, and we'll see you next time. Have a good day.